You are standing on solid ground right now. Maybe a floor, maybe earth, maybe concrete. You feel it beneath your feet. You trust it. It is such a fundamental part of your existence that you have probably never questioned it. Every world you have ever imagined visiting has a surface. Mars has red rock. The moon has grey dust. Even Venus, with its crushing atmosphere and acid rain, has ground you could theoretically stand on for a few agonizing seconds before being cooked alive. But Jupiter? Jupiter has no ground, no floor, no bottom. There is nowhere to land. And that is just the beginning of why approaching this monster of a planet would be the most elaborate suicide mission in the history of the cosmos. Before we descend into the abyss, let us establish what we are dealing with. Jupiter is not merely a large planet. It is a category error made manifest when astronomers first turned their telescopes toward the night sky in the 1600s and saw this brilliant wandering star. They had no framework for understanding what they were actually looking at. They assumed it was simply another world, perhaps a bit larger than Earth. They were wrong by a factor that defies intuition. Jupiter contains more mass than all the other planets in our solar system combined. Not just more than Mars or Saturn individually, more than Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune put together, with room to spare. If you rolled every single planet, moon, asteroid, and comet in our solar system into one giant ball, that ball would still only be about 40% of Jupiter's mass. Its diameter stretches 142,984 kilometers, roughly 11 times wider than Earth. More than 1,300 Earths could fit inside Jupiter's volume. If Jupiter were hollow, you could pour our entire planet inside it over 1,000 times and still have room for more. To put this in perspective, consider a journey across Jupiter's equator. If you could somehow drive a car at highway speed, 100 kilometers per hour, it would take you nearly 6 years of continuous driving to complete one lap. To drive around Earth at the same speed takes only 17 days. Jupiter is not just bigger than Earth. It exists on a completely different scale. The planet rotates faster than any other in the solar system, completing one full rotation in just under 10 hours. Despite being 11 times wider than Earth, a day on Jupiter is less than half as long. This rapid rotation, combined with the fluid nature of the planet, causes Jupiter to bulge noticeably at its equator. The planet is about 6.5% wider at the equator than at the poles, giving it a slightly squashed appearance when viewed from the side. But here is where it gets strange. Despite being so incomprehensibly massive, Jupiter is made almost entirely of the lightest elements in the universe, hydrogen and helium, the same stuff that makes up the Sun. In fact, Jupiter's composition is nearly identical to our star. It has the same ingredients, the same recipe. Jupiter is, in a very real sense, a failed star. It failed because it needed to be about 75 times more massive to ignite nuclear fusion in its core. Jupiter was the first planet to form after the Sun ignited, gobbling up most of the leftover material from the solar nebula, but it simply ran out of gas before it could become a second sun. We live in a solar system that came tantalizingly close to being a binary star system. The night sky on Earth could have had 2 suns, but Jupiter remained frozen in that almost there state, a ball of primordial gas that never quite made it to stellar ignition. And because of that, it exists as something profoundly alien, a world with no solid surface, just an endless ocean of atmosphere that gradually, seamlessly transitions into something even stranger the deeper you go. Let us talk about what you would actually encounter if you tried to land on Jupiter. Imagine you are an astronaut in a spacecraft approaching the giant planet. You have survived the 6-month journey from Earth. You have crossed the asteroid belt. You have watched Jupiter grow from a bright point of light into a disk, then into something that fills your entire field of view. As you approach within 300,000 kilometers, before you even reach the outermost wisps of atmosphere, you begin to die. Not from heat, not from pressure, not from any of the things you might expect, from radiation. Jupiter possesses the most powerful magnetic field of any planet in our solar system, roughly 20,000 times stronger than Earth's. This magnetic field, generated by the churning ocean of liquid metallic hydrogen deep inside the planet, creates a magnetosphere so vast that if you could see it from Earth with your naked eyes, it would appear larger than the full moon in the sky. Within this magnetosphere, Jupiter has trapped and accelerated charged particles to nearly the speed of light, creating radiation belts that make Earth's Van Allen belts look like a gentle spring breeze. The radiation intensity near Jupiter exceeds what any living thing could survive by orders of magnitude. When the Pioneer 10 spacecraft flew past Jupiter in December 1973, it passed through the inner radiation belts at a distance of 2.85 Jupiter radii from the planet's center. The probe received an integrated dose of 200,000 rads from electrons and 56,000 rads from protons during its passage. For context, a whole body dose of 500 rads is fatal to humans. Pioneer 10 received hundreds of times that amount. The radiation was 10 times more powerful than mission designers had predicted. They genuinely feared the spacecraft would not survive. It limped through the belts, suffering glitches in its electronics, saved largely by the fact that Jupiter's magnetosphere happened to be in a favorable orientation during the flyby. Any human astronaut, even one protected by the most advanced shielding we can currently build, would receive a lethal radiation dose long before reaching Jupiter's atmosphere. The charged particles would tear through cells, shredding DNA, destroying tissue. Death would come quickly, but not quickly enough to be merciful. So let us assume, for the sake of this thought experiment, that we have built a spacecraft with miraculous radiation shielding, something that can protect you from the particle storm. You push through the radiation belts, past the inner moons, and approach the cloud tops of Jupiter itself. Now, the real nightmare begins. Jupiter's atmosphere begins subtly, almost imperceptibly. Unlike Earth, where there is a clear boundary between space and air, Jupiter's outer atmosphere simply becomes gradually denser as you descend. There is no moment where you cross from vacuum into gas. It is a continuous gradient, the universe's largest fade from nothing into something. At the altitude where pressure equals about 0.1 bar, 1/10 of Earth's sea level pressure, you find yourself at what scientists define as the top of Jupiter's atmosphere. You are still technically in space by most definitions, but hydrogen and helium molecules are now bumping against your spacecraft in increasing numbers. You begin to fall. Jupiter's gravity pulls you downward with a force 2.5 times stronger than Earth's gravity. If you weigh 180 pounds on Earth, you would weigh 450 pounds on Jupiter. if there were anywhere to stand, which there is not. This relentless gravitational acceleration combines with the near vacuum around you to accelerate your spacecraft to terrifying velocities. By the time you reach the cloud tops, you are traveling at approximately 180,000 kilometers per hour, or about 50 kilometers per second. This is faster than any bullet, faster than any man-made object has ever traveled through an atmosphere. You are moving at comet-like velocities, slamming into Jupiter's upper atmosphere with the kinetic energy of a small nuclear weapon. This is exactly what happened to the Galileo Probe on December 7th, 1995. That date is worth remembering. December 7th, 1995, the only time in human history that a spacecraft successfully entered the atmosphere of an outer planet and transmitted data back to Earth. Every measurement we have of conditions inside Jupiter comes from those 58 minutes. Every model we build of the planet's atmosphere is calibrated against that single descent. One probe, 1 hour, one window into a world. The Galileo Probe, a 339-kilogram capsule designed specifically for this suicide mission, hit Jupiter's atmosphere at 47.8 kilometers per second. In the first 2 minutes of its descent, the probe experienced a peak deceleration of 228 Gs, meaning the probe and everything inside it momentarily weighed 228 times their normal weight. No human could survive this. The force would liquefy your internal organs. The friction of passage through the upper atmosphere generated temperatures that peaked at approximately 15,500 degrees Celsius, nearly 3 times hotter than the surface of the Sun. The probe's carbon phenolic heat shield, designed to absorb this punishment, lost more than half its mass during descent. 80 kilograms of material simply ablated away, vaporized into the surrounding atmosphere. But the probe survived. It slowed from 47 kilometers per second to subsonic speeds in less than 2 minutes, deployed its parachute, and began transmitting data back to the orbiter overhead. For 58 minutes, the Galileo Probe descended into Jupiter, sending back measurements of temperature, pressure, wind speed, and atmospheric composition. It was the first and only object humanity has ever sent into the atmosphere of an outer planet, and then it went silent. The probe's transmitter failed at a depth of approximately 160 kilometers below its entry point, at a pressure of about 23 atmospheres, 23 times Earth's sea level pressure. The cause of death was almost certainly the crushing pressure combined with temperatures that had climbed to around 150 degrees Celsius. But here is what makes Jupiter truly terrifying. The Galileo Probe had barely scratched the surface. It penetrated less than 0.2% of the distance to Jupiter's center before being destroyed. The descent was just beginning. Let us continue the journey that the Galileo Probe could not complete. You are falling through Jupiter's atmosphere, having somehow survived the entry heating that destroyed most of your heat shield. The sky above you is still bright, tinged with the rust-red and cream-white bands of ammonia ice clouds. You can see lightning flickering in the distance, bolts thousands of kilometers long, illuminating cloud formations the size of continents. At about 1 bar of pressure, equivalent to Earth's surface pressure, you pass through the first major cloud layer. Crystals of frozen ammonia suspended in hydrogen gas. The temperature here is around minus 110 degrees Celsius. Cold, but not impossibly so. The pressure is manageable. For a brief moment, conditions almost seem survivable. This is deceptive. You continue falling. The hydrogen-helium atmosphere is thick enough now to provide significant drag, slowing your descent. But Jupiter's gravity keeps pulling you deeper. You pass through a second cloud layer, this one made of ammonium hydrosulfide, giving the clouds a brownish tint. Then deeper still, into a third layer where water ice forms clouds similar to Earth's. At about 5 bars of pressure, 5 times Earth's sea level, something unexpected happens. The temperature rises to near freezing, then above it. Jupiter's interior is warm, heated by the slow gravitational compression of the planet and residual heat from its formation 4.6 billion years ago. The temperature will only increase from here. At 10 bars, you have descended roughly 100 kilometers below the cloud tops. Light from the distant sun can no longer reach you. You are in total darkness, interrupted only by the occasional flash of lightning. The temperature has risen to around 20 degrees Celsius. Room temperature. If it were not for the crushing pressure, you could almost breathe. But the pressure is crushing. 10 times Earth's atmosphere means 10 times the force, pressing on every square centimeter of your body. Your eardrums would have long since ruptured. Your sinuses would be collapsing. Even inside a pressure-resistant craft, the stress on your hull is becoming extreme. You fall deeper. At 100 bars, 100 times Earth's pressure, you have descended roughly 300 kilometers. The temperature has climbed to several hundred degrees Celsius. The hydrogen around you is no longer behaving like a normal gas. It is becoming a supercritical fluid, something that is simultaneously gas and liquid with properties of both. There is no clear transition point, no surface to hit. The atmosphere simply becomes denser and denser, hotter and hotter. At 1,000 bars, 1,000 times Earth's pressure, you have fallen perhaps 1,000 kilometers below the clouds. The temperature exceeds 1,000 degrees Celsius. Any conventional spacecraft materials have long since softened and deformed. Steel would be glowing red hot and beginning to lose structural integrity. But there is still no surface, no bottom, nothing to land on. The Galileo Probe lasted 58 minutes and reached 23 bars before being destroyed. You have already passed through pressures 40 times greater than that, and you are not even a fraction of the way to Jupiter's center. At a depth of around 7,000 kilometers below the cloud tops, something extraordinary begins to happen. The pressure has reached approximately 2 million times Earth's atmospheric pressure. The temperature has climbed to around 6,000 degrees Celsius, hotter than the surface of the sun. But under these incomprehensible conditions, the hydrogen around you undergoes a phase transition unlike anything found on Earth. The pressure is so intense that it strips electrons from hydrogen atoms and forces them to flow freely between nuclei. The hydrogen becomes metallic. This is not a metaphor. The hydrogen literally becomes a metal, conducting electricity and heat like liquid mercury. It glows with its own incandescent light, a vast ocean of shimmering metallic fluid with no surface and no bottom, just an endless gradient of ever-increasing pressure and temperature. You have entered the largest ocean in the solar system, but it is an ocean made of metal that exists at temperatures that would vaporize rock. Physicists Eugene Wigner and Hilliard Bell Huntington first predicted the existence of metallic hydrogen in 1935, calculating that hydrogen would take on metallic properties at pressures around 25 GPa, about 250,000 times Earth's atmospheric pressure. They were roughly correct. Inside Jupiter, these conditions are not only met, but exceeded by orders of magnitude. The metallic hydrogen layer extends from about 7,000 kilometers below the cloud tops to perhaps 60,000 kilometers down, spanning more than 80% of Jupiter's radius. This ocean is responsible for Jupiter's powerful magnetic field, as the metallic hydrogen churns and convects, driven by heat escaping from the planet's interior. It generates electrical currents that produce the strongest planetary magnetic field in our solar system. At this depth, the pressure reaches approximately 40 million times Earth's atmosphere. The temperature has climbed to around 10,000 to 20,000 degrees Celsius. No material known to science can survive these conditions. No technology we can conceive would function here. Any spacecraft, any probe, any theoretical structure would have been crushed, melted, and dissolved thousands of kilometers above you. And yet, you are still not at the center. You are still falling. Deep within Jupiter, at distances greater than 60,000 kilometers below the visible cloud tops, scientists believe there exists something like a core. But even here, Jupiter refuses to conform to expectations. For decades, planetary scientists assumed Jupiter had a dense, compact core of rock, metal, and ice, somewhere between 8 and 15 times the mass of Earth, sitting at the very center of the planet like a cosmic seed around which the gas giant grew. The standard model of planetary formation required such a core. First, the solid materials clumped together. Then they accumulated enough mass to gravitationally capture hydrogen and helium from the surrounding nebula. But when NASA's Juno spacecraft began orbiting Jupiter in 2016 and making precise measurements of the planet's gravitational field, it found something puzzling. The gravity data suggested that Jupiter's core was not a compact ball of dense material. Instead, it appeared to be diffuse, spread out, almost diluted. Scientists began describing Jupiter's core as fuzzy, the heavy elements, the rock and metal and ice that should have sunk to the center, appear to be distributed across nearly half of Jupiter's diameter, gradually blending into the metallic hydrogen above. There is no clear boundary between core and mantle. No surface. No discrete layers like you would find inside a rocky planet. One hypothesis suggests that early in Jupiter's history, a planetary body roughly 10 times the mass of Earth collided with the young gas giant, smashing into its then compact core and dispersing the heavy elements throughout the interior. Another hypothesis proposes that the core never fully differentiated in the first place, that the heavy elements were distributed diffusely from the beginning. Whatever the explanation, the result is the same. There is nothing to land on, no surface at any depth. The atmosphere simply becomes denser and hotter and stranger until eventually you reach a region where the pressure exceeds 40 million atmospheres and the temperature approaches 20,000 degrees Celsius, conditions that vaporize anything that exists. At the very center of Jupiter, models suggest pressures might reach 100 million times Earth's atmosphere, with temperatures around 24,000 degrees Celsius. At these conditions, matter exists in exotic states that we cannot recreate in any laboratory on Earth. The distinction between solid, liquid, and gas becomes meaningless. There is no bottom. There is no ground. There is only pressure, heat, and the crushing weight of a world that never quite became a star. Let us be clear about what we have described. If you attempted to descend into Jupiter in the most advanced spacecraft humanity could build, you would die in stages. First, the radiation belts would kill you long before you reached the atmosphere. If you somehow survived that, the entry heating would vaporize your spacecraft. If your heat shield miraculously held, the growing pressure would crush you. If your pressure vessel somehow withstood thousands of atmospheres, the rising temperature would cook you. If your cooling system somehow functioned at thousands of degrees, the transition into metallic hydrogen would dissolve your spacecraft into its constituent atoms. There is no depth at which survival is possible. There is no depth at which landing is possible. There is nothing to land on. The Galileo Probe, the only object humanity has ever sent into Jupiter's atmosphere, lasted 58 minutes and reached a depth of about 160 kilometers before being destroyed by conditions that were, relative to what lies below, almost gentle. It barely penetrated the planet's outermost skin. Jupiter's radius is about 70,000 kilometers. The Galileo Probe reached 0.23% of the way to the center. It was like dropping a pebble into the Pacific Ocean and watching it sink 2 feet before disintegrating. And yet, there is something even more unsettling to consider. Jupiter is not content simply to kill anything that enters it. Jupiter is also impossible to escape. Jupiter's escape velocity, the speed required to break free of its gravitational pull from the cloud tops, is approximately 60 kilometers per second. For comparison, Earth's escape velocity is about 11 kilometers per second. To leave Jupiter, you would need to accelerate to more than 5 times the speed required to leave Earth. No rocket humanity has ever built could achieve this. No propulsion system we have ever conceived could generate enough thrust to lift a spacecraft out of Jupiter's gravity well, even if you could somehow survive a descent into Jupiter's atmosphere, even if you could somehow hover at some arbitrary depth, you would be trapped. The gravity that pulled you in would never let you go. This is one reason why NASA deliberately crashed the Galileo orbiter into Jupiter at the end of its mission in 2003. The spacecraft had not been sterilized before launch, meaning it potentially carried Earth bacteria that could contaminate Jupiter's moons, particularly Europa, with its subsurface ocean that might harbor life. Rather than risk an eventual accidental collision with a moon, mission controllers sent Galileo plunging into Jupiter's atmosphere, where it was crushed, melted, and dissolved into the planet's interior. The spacecraft's final transmission came at 1857 UTC on September 21st, 2003. It was traveling at 30 miles per second when contact was lost. Somewhere deep within Jupiter, the atoms that were once Galileo are now dispersed through the metallic hydrogen ocean, part of the giant planet forever. Here is the paradox of Jupiter. This world that cannot be landed on, that cannot be explored in person, that destroys everything that enters it, might be the reason you exist at all. Jupiter has been called the vacuum cleaner of the solar system. Its immense gravity attracts and captures asteroids and comets that wander too close, either swallowing them directly or flinging them out of the solar system entirely. In July 1994, astronomers watched as comet shoemaker Levy 9, broken into 21 major fragments by tidal forces during a previous close approach, slammed into Jupiter over the course of 6 days. The impacts were spectacular. Fragment G alone released energy equivalent to 6 million megatons of TNT, roughly 600 times the world's entire nuclear arsenal. The resulting fireball rose 3,000 kilometers above Jupiter's cloud tops. The dark scars left in the atmosphere were larger than Earth and remained visible for months. Had that comet struck our planet instead, it would have been an extinction-level event, potentially ending all complex life on Earth. Scientists estimate that Jupiter experiences between 2,000 and 8,000 times more cometary impacts than Earth. It absorbs punishment that might otherwise be directed at us. Some researchers have argued that without Jupiter, life on Earth might never have had the billions of years of relative stability needed to evolve from single-celled organisms into intelligent beings. This is not universally accepted. Some simulations suggest that Jupiter might actually increase the rate of asteroid impacts on Earth by gravitationally nudging objects onto collision courses with our planet that they would not otherwise follow. The truth is probably complicated. Jupiter both protects and endangers us, depending on the specific object and its trajectory. But regardless of its precise role, Jupiter shaped our solar system. It was the first planet to form after the Sun, and its gravitational influence during the early solar system determined where other planets could form, which planetesimals would survive, and what kind of cosmic environment Earth would inhabit. We cannot land on Jupiter. We cannot survive Jupiter. But in a very real sense, we might not exist without it. Consider for a moment what makes other worlds in our solar system landable. Mercury, the smallest planet, has a surface of ancient cratered rock baked by the nearby Sun. You could land on Mercury. The temperatures would kill you, ranging from 430 degrees Celsius in the Sun to minus 180 degrees Celsius in shadow. But there is ground to stand on. Venus has a surface of volcanic rock hidden beneath crushing clouds of sulfuric acid. The pressure at the surface is 92 times Earth's, equivalent to being 900 meters underwater. The temperature is 465 degrees Celsius, hot enough to melt lead. The Soviet Venera landers survived on Venus's surface for between 23 and 127 minutes before being destroyed by the heat. But they landed. There was ground. Mars has a surface of rust-red rock and dust. The pressure is less than 1% of Earth's. The temperature averages minus 60 degrees Celsius. Humans would need pressure suits and heating systems, but they could walk on Mars. Multiple rovers have driven across its surface. Landers have scooped its soil. There is ground to stand on. Even Titan, Saturn's largest moon, has a surface. It is covered in frozen organic compounds and pooled liquid methane with a thick nitrogen atmosphere. The Huygens probe landed on Titan in 2005, touching down on a surface of water ice covered in hydrocarbon sediments. There was ground to stand on. Every world we have explored up close has a surface. Every world we have imagined visiting has a floor. Our entire conceptual framework for planetary exploration is built around the assumption that exploration means going somewhere and stopping. Jupiter breaks this assumption. There is nowhere to stop. NASA's Juno spacecraft has been orbiting Jupiter since 2016, making close passes over the planet's poles to study its interior, atmosphere, and magnetic field. Unlike the Galileo Probe, Juno was designed to survive in Jupiter's radiation environment for an extended mission, using special radiation-hardened electronics housed in a titanium vault. Even so, the radiation takes its toll. Juno's cameras have degraded over time. Its instruments show the cumulative damage of billions of high-energy particles slamming into sensitive electronics. The spacecraft is slowly dying, bit by bit, eroded by the very environment it was sent to study. Every orbit brings new damage. Every close pass over Jupiter's poles exposes Juno to another dose of radiation. The spacecraft's systems were designed with margins, with redundancies, with the expectation that things would fail. And things have failed. But enough remains functional to continue the mission, to gather data, to send images back to Earth that transform our understanding of the giant planet. Juno's orbit is highly elliptical, carrying it from close passes just 4,000 kilometers above Jupiter's cloud tops to distances of millions of kilometers. This orbit was chosen deliberately. The close passes allow detailed observations of the planet's atmosphere and magnetic field. The distant portions of the orbit allow the spacecraft to escape the worst of the radiation belts, giving its electronics time to recover between exposures. It is a dance with death, repeated every orbit. Dive in, gather data, retreat, transmit, recover, then dive again. Juno has performed this dance dozens of times and will continue until its systems finally fail beyond recovery. Juno has revealed Jupiter to be even stranger than anyone expected. Its core is fuzzy and diffuse. Its atmosphere is not neatly layered, but turbulent and dynamic, with storms extending hundreds of kilometers deep. Its magnetic field is lumpy and asymmetrical, nothing like the simple dipoles scientists anticipated. Clusters of cyclones, each larger than Earth, swirl in stable geometric patterns around its poles, defying explanation. Jupiter keeps surprising us. It keeps refusing to fit our models. It remains, in many ways, as mysterious as it was when Galileo first trained his telescope on it 4 centuries ago. In January 1610, Galileo Galilei pointed his crude telescope at Jupiter and saw 4 points of light hovering near the planet. Over the following nights, he watched these points move, changing position relative to each other and to Jupiter itself. He realized they were moons, orbiting the giant planet just as Earth's moon orbits us. This observation helped shatter the geocentric model of the universe. Here was proof that not everything revolved around Earth. Here was a miniature solar system, visible through a simple telescope, demonstrating that other worlds could have their own satellites. 400 years later, we have sent spacecraft to those same moons that Galileo discovered. We have mapped their surfaces. We have measured their compositions. We have found evidence of subsurface oceans that might harbor life. But Jupiter itself remains beyond our reach. We can orbit it. We can observe it. We can send probes to die in its atmosphere. But we cannot land on it. And we still cannot land on it. There is a profound humility in this limitation. Humanity has walked on the moon. We have sent rovers to Mars. We have landed probes on Venus, Titan, asteroids, and comets. We have extended our reach across billions of kilometers, touching worlds that our ancestors could only see as points of light. But Jupiter, remains untouchable, not because we lack the will, not because we lack the funding, not because we lack the technology to reach it. We can reach it. We have reached it multiple times. We simply cannot survive what we find when we arrive. Jupiter is a monument to cosmic indifference. It does not care about our aspirations. It does not care about our ingenuity. It exists on a scale and under conditions that our biology and our technology cannot match. It will crush, melt, dissolve, and irradiate anything we send into it. And it will do so without malice, without purpose, simply because that is what Jupiter does. There is no surface to plant a flag on, no vista to photograph with human eyes, no samples to bring home. Jupiter is experienced only through proxies, through machines that we sacrifice to its depths, through data transmitted from orbit before spacecraft succumb to radiation damage. And yet, there is something magnificent about a world that cannot be conquered. In an age when it sometimes seems that human technology can overcome any obstacle, Jupiter stands as a reminder that the universe is vast, ancient, and fundamentally unconcerned with our presence. Jupiter has existed for 4.6 billion years. It formed from the same cloud of gas and dust that made our sun, carrying within it the primordial chemistry of the early solar system. Its atmosphere has been churning, its storms raging, its magnetic field pulsing, for longer than life has existed on Earth. It will still be there, essentially unchanged, long after humanity is gone. When you look up at the night sky and see that bright wandering star, you are looking at a world that defies everything you know about planets. No ground, no landing site, nothing but an endless descent into pressure, heat, and dissolution. Jupiter is impossible to land on, and perhaps that is exactly as it should be. The next time you stand on solid ground, take a moment to appreciate it. Feel the floor beneath your feet, the rock, the concrete, the earth. Feel its solidity, its stability, its willingness to bear your weight. Then look up. Somewhere out there, 5 times farther from the sun than Earth, a world made of gas and lightning and liquid metal is spinning through the void. A world where gravity never ends, where pressure never stops increasing, where the concept of landing has no meaning. A world that protects us, a world that could destroy us, a world that we can visit but never touch. But we are not finished yet. There is more to understand about why Jupiter is so fundamentally hostile, so completely and totally impossible for human presence. Let us talk about the storms. You have probably seen images of Jupiter, those swirling bands of orange and white, the alternating stripes that wrap around the planet like the stripes on a cosmic candy. They look almost peaceful from a distance, abstract, artistic. They are anything but peaceful. Those bands are not static patterns painted on Jupiter's atmosphere. They are jet streams, rivers of gas flowing at hundreds of kilometers per hour in alternating directions around the planet. The light-colored zones are regions where gas is rising from the depths. The dark belts are regions where gas is sinking. The entire visible surface of Jupiter is a dynamic, churning maelstrom of atmospheric motion, and nestled within this chaos are storms that make every hurricane in Earth's history look like a gentle breeze. The Great Red Spot has been raging for at least 360 years, and possibly much longer. When astronomers first began systematically observing Jupiter in the 1600s, they recorded a similar feature. Whether it is the same storm or predecessor remains debated, but the current Great Red Spot has been continuously observed since at least 1830. This single storm is larger than Earth. It was even larger in the past, gradually shrinking over the centuries, but it still measures approximately 16,000 kilometers across, roughly 1.3 times our planet's diameter. Wind speeds at its edges exceed 400 miles per hour, faster than any hurricane ever recorded on Earth. On our planet, hurricanes die when they move over land. The friction with the surface disrupts their circulation, cutting off their energy supply. Within days, even the most powerful storm dissipates into scattered rain and fading winds. Jupiter has no land, no surface, nothing to slow the storms down. The Great Red Spot has persisted for centuries because there is nothing to stop it. It simply spins and spins, an anticyclonic vortex fed by the heat rising from Jupiter's interior and the differential rotation of the planet's atmosphere. It has absorbed smaller storms, grown, shrunk, brightened, and faded, but it has never stopped. Recent data from the Juno spacecraft suggests the Great Red Spot extends approximately 300 to 500 kilometers below the visible cloud tops. This is shallow compared to Jupiter's total size, but it is still deep enough that the storm involves pressures and temperatures far beyond anything found on Earth. The energy contained in the Great Red Spot exceeds anything humans have ever experienced or created. And the Great Red Spot is just one storm among many. Jupiter's poles are ringed by clusters of cyclones, each one larger than Earth, arranged in stable geometric patterns. 8 cyclones surround the North Pole. 5 surround the South Pole. These patterns have remained stable since Juno first observed them, each massive storm locked into position by the dynamics of its neighbors. We do not fully understand why these patterns are stable. We do not fully understand how these storms form or what maintains them. Jupiter's atmosphere is a system so complex, so driven by forces we are only beginning to measure, that our models continually fail to predict what we observe. You cannot. No one can. Nothing we build, nothing we design, nothing we imagine can land on something that has no bottom, can survive conditions that exceed the limits of matter itself. But we can watch, we can measure, we can send our machines into the abyss and learn from what they report before they die. And that, perhaps, is the best we can hope for. Here is another problem with Jupiter that we have not yet discussed: the cold. This might seem counterintuitive. We have spent considerable time describing the crushing heat deep inside the planet, temperatures that exceed the surface of the sun. But at the cloud tops, where any spacecraft must first enter, Jupiter is brutally cold. The temperature at the 1 bar pressure level, the arbitrary altitude scientists use as Jupiter's surface, is approximately minus 110 degrees Celsius. That is colder than the coldest temperature ever recorded in Antarctica. That is colder than liquid nitrogen. That is cold enough to freeze nearly every substance humans have ever encountered. But the cold does not last. As you descend, the temperature rises rapidly. Jupiter's interior is hot, heated by gravitational compression and residual thermal energy from the planet's formation. The temperature gradient is steep. Within a few hundred kilometers, you pass from deadly cold to room temperature to blistering heat. This creates a strange phenomenon. Somewhere inside Jupiter, at some depth that varies with location and conditions, The temperature and pressure are actually similar to Earth's surface, around 5 bars of pressure. The temperature reaches approximately 20 degrees Celsius. It is warm, almost comfortable. You could almost imagine surviving, but you cannot survive because the pressure at that depth would crush you regardless of the temperature. And if you somehow solved the pressure problem, you would still be surrounded by hydrogen gas with no oxygen to breathe. And even if you solved the breathing problem, you would be falling continuously with no ground to stop your descent, sinking ever deeper into conditions that only become more extreme. Jupiter tantalizes with these moments of almost survivability. There is a layer where the pressure is manageable, a layer where the temperature is pleasant, a layer where the winds are calm. But these layers never overlap. The conditions that would allow human survival never coincide. Jupiter offers no haven, no rest stop, no refuge. Consider the wind. We mentioned the jet streams, the alternating bands of eastward and westward flowing gas that create Jupiter's striped appearance. But we did not fully convey what these winds mean for anything attempting to pass through them. The Galileo Probe measured wind speeds during its descent in 1995. At the cloud tops, winds blew at approximately 230 miles per hour. This is already faster than the strongest winds in any Earth hurricane. But as the probe descended, the winds did not decrease. They increased. At 10 miles below the clouds, winds reached 313 miles per hour. At 17 miles down, 360 miles per hour. At 28 miles down, 391 miles per hour. The winds remained at roughly 400 miles per hour all the way to the probe's destruction at a depth of about 100 miles. These are not surface winds. These are not gusts or squalls. These are the sustained permanent motion of Jupiter's atmosphere, a world-girdling river of gas moving faster than the speed of sound in Earth's atmosphere. Scientists had expected the winds to decrease with depth. They theorized that Jupiter's atmospheric circulation was driven by solar heating, like Earth's weather. If that were true, the winds should have diminished as the probe descended below the zone where sunlight penetrated. They were wrong. The Galileo Probe's measurements revealed that Jupiter's winds are not driven by the sun. They are driven from below, by the immense heat escaping from the planet's interior. Jupiter generates nearly twice as much energy as it receives from the sun, radiating the excess heat from its formation and gravitational contraction. This heat rises through the atmosphere, driving convection, powering storms, and maintaining wind speeds that persist far deeper than anyone had predicted. Some scientists now believe Jupiter's winds extend thousands of kilometers into the interior, perhaps all the way down to the metallic hydrogen layer. The entire planet might be in constant motion, a world-sized dynamo of churning gas with no calm zone anywhere. Imagine trying to fly through this. We should also discuss the lightning. Jupiter has lightning. We knew this before Galileo, from radio emissions detected by Earth-based telescopes in the 1970s. But the Galileo orbiter and probe provided the first direct observations, photographing flashes in Jupiter's night-side atmosphere and measuring their energy output. Jovian lightning is not like Earth lightning. On Earth, lightning is generated when water droplets and ice crystals in thunderstorms collide, separating electrical charges until the buildup becomes too great and discharges in a brilliant flash. Our lightning occurs in clouds a few kilometers above the surface, at temperatures cold enough for water to freeze. Jupiter has water clouds too, deep in its atmosphere. Lightning occurs there. But Jupiter also has lightning in places where water cannot exist. Juno discovered shallow lightning occurring high in Jupiter's atmosphere, in regions where temperatures are far too cold for liquid water. This lightning appears to be generated by collisions between ammonia ice crystals, creating electrical discharges in ammonia clouds rather than water clouds. Jupiter also has superbolts. Lightning strikes far more powerful than anything on Earth. Some Jovian lightning releases more energy in a single flash than the most powerful lightning on our planet. The precise energies remain debated, with estimates varying widely, but some observations suggest individual strikes carrying the energy of small nuclear devices. Lightning is beautiful from a distance. It is deadly up close. And on Jupiter, lightning occurs everywhere, at all altitudes, through all the layers you would need to traverse. Let us pause and consider the timeline of a hypothetical descent. You enter Jupiter's atmosphere at the cloud tops, somehow surviving the radiation belts and entry heating. You are falling through ammonia ice clouds. The sky above is still visible, though the sun is just a small, bright point 480 million miles away. After 5 minutes, you have descended to approximately 2 bars of pressure, twice Earth's atmospheric pressure. You are passing through brownish clouds of ammonium hydrosulfide. The temperature is still cold, around minus 70 degrees Celsius. Your descent rate has slowed as atmospheric drag increases. After about 12 minutes, you reach 5 bars. The temperature has risen to near freezing. You are in the water cloud layer. Everything is dark now. Sunlight cannot penetrate this far. You see only blackness, interrupted by distant flashes of lightning. After about an hour, you reach approximately 10 bars. The temperature is 20 degrees Celsius. Comfortable if you ignore the pressure crushing your spacecraft. You are completely blind without artificial lighting. The hydrogen atmosphere around you is becoming a supercritical fluid, neither truly gas nor liquid. After several hours, you have descended hundreds of kilometers. The pressure exceeds 1,000 bars. The temperature exceeds 1,000 degrees Celsius. No conventional material can survive these conditions. If your spacecraft had not already failed, it is failing now. After perhaps 12 hours of descent, assuming your indestructible hypothetical craft somehow continues, you approach the metallic hydrogen layer at about 7,000 kilometers depth. The pressure is now millions of times Earth's atmosphere. The temperature exceeds the surface of the sun. You are no longer falling through gas. You are sinking through a glowing ocean of liquid metal. The descent continues. Days pass. Weeks. The pressure continues to increase. The temperature continues to rise. You sink ever deeper into conditions that make the core of the sun seem almost tame by comparison. Eventually, at some depth that we cannot precisely calculate, you stop sinking, not because you have hit a surface, but because the material around you has become so dense that your spacecraft is now buoyant. You float, suspended in a layer of ultra-dense matter, surrounded by darkness and crushing force, tens of thousands of kilometers from anything resembling normal space. There is no escape. There is no rescue. There is no communication with the outside universe. Even if you could somehow survive these conditions, even if your hypothetical spacecraft could withstand forces that would crush a submarine into atoms, you would be trapped forever in Jupiter's interior. This is what it means to land on Jupiter. You cannot land. You can only sink until you dissolve. There is one more thing to consider, something that often goes unmentioned in discussions of Jupiter exploration. Time. Jupiter is far away, very far. At its closest approach to Earth, Jupiter is approximately 588 million kilometers distant. At its farthest, when Earth and Jupiter are on opposite sides of the Sun, the distance exceeds 960 million kilometers. Even at the speed of light, signals take between 33 and 53 minutes to travel between Earth and Jupiter, depending on orbital positions. This means any spacecraft operating at Jupiter experiences a minimum round-trip communication delay of over an hour. If something goes wrong, mission controllers on Earth cannot respond in real time. They receive the bad news half an hour after it happens, and their corrective commands arrive half an hour after they send them. The Galileo Probe was programmed in advance. It had no human controller guiding it through Jupiter's atmosphere. It followed its instructions, transmitted its data to the orbiter overhead, and died alone. For the Galileo Probe, this meant pre-programmed instructions executed without deviation. The probe entered the atmosphere exactly as designed, measured exactly what it was designed to measure, transmitted exactly as long as it could, and then went silent. There was no mission control commanding it through the descent. There was no voice guiding it deeper into the planet. The probe did its job and died, alone in the darkness, 480 million miles from the nearest human being. When the probe's signal finally failed at 23:01 UTC on December 7th, 1995, the mission team on Earth did not know it immediately. The signal traveled at the speed of light, taking about 52 minutes to reach Earth. By the time the controllers realized the probe had gone silent, it had already been dead for nearly an hour. Crushed by pressures it was never designed to survive. This is what it means to explore the impossible. You plan, you build, you launch, and then you wait, watching data arrive from the past, knowing that whatever you see has already happened, knowing that you cannot change it, knowing that your machine is on its own. The spacecraft that explore Jupiter must be autonomous in ways that no Earth-based vehicle has ever been. They must make decisions without human input. They must solve problems before we even know the problems exist. And ultimately, they must accept their destruction, transmitting data until the moment the physics of Jupiter finally overwhelms their engineering. This is the nature of deep space exploration. It is not adventure. It is not glory. It is sending machines to die so that we can learn. There have been proposals over the years for crewed missions to the Jupiter system. Not to land on Jupiter itself, of course, but to orbit it, to study its moons up close, perhaps eventually to land on Europa or Ganymede or Callisto. These proposals always run into the same problem: radiation. A human astronaut in Jupiter's magnetosphere would receive a lethal radiation dose within hours. Even at the orbit of Callisto, the outermost of the 4 Galilean moons, radiation levels are dangerously high. Any crewed mission to the Jupiter system would require radiation shielding far more massive than anything we have ever launched into space. And then there is the journey itself. At optimal launch windows, a spacecraft can reach Jupiter in about 2 years using gravity assists from other planets. A direct trajectory takes longer. Any crewed mission would need to carry enough supplies, water, oxygen, and food for years of travel, plus time in the Jupiter system, plus the return journey. The spacecraft would be massive. The mission would be incredibly expensive. The risks would be extraordinary. And at the end of it all, the astronauts would not be able to land on Jupiter. They would orbit it, study it from a distance, perhaps visit its moons, but Jupiter itself would remain forever beyond their reach. Some things cannot be touched. Some places cannot be visited. Jupiter reminds us that there are limits to human presence in the cosmos, places where our biology and our technology simply cannot go. This is not a failure. It is a fact. So why bother? If Jupiter cannot be landed on, cannot be explored in person, cannot be conquered or colonized, or made useful in any conventional sense, why do we keep sending spacecraft to study it? Because Jupiter is a key to understanding how worlds form. Jupiter was the first planet. Before Earth, before Mars, before any of the rocky inner worlds, Jupiter coalesced from the same cloud of gas and dust that formed our Sun. It contains primordial material from the earliest moments of the solar system's existence. Its composition, its structure, its atmosphere preserve a record of conditions that existed 4.6 billion years ago. By studying Jupiter, we learn about the birth of planets. We learn about the processes that separate heavy elements from light ones, that drive atmospheric circulation, that generate magnetic fields. We learn about gas giants in general, a category of planet that may be the most common in our galaxy. When astronomers discovered the first exoplanet around a sun-like star in 1995, it was a gas giant. A hot Jupiter, they called it. A massive world orbiting impossibly close to its parent star. Since then, we have discovered thousands of exoplanets, and gas giants appear everywhere. They seem to be a fundamental outcome of planetary formation. But we only have one gas giant we can study up close. One gas giant where we can send probes, measure gravitational fields, analyze atmospheric composition. Jupiter is our laboratory for understanding an entire category of cosmic objects. And there is another reason we study Jupiter, a more personal one. Jupiter has moons. Europa orbits Jupiter every 3.5 days at a distance of about 671,000 kilometers from the planet's center. It is one of 4 large moons that Galileo discovered in 1610, the same moons that helped prove the Copernican model of the solar system. Europa is covered in water ice. Its surface is crossed by reddish cracks and ridges, fractured and refrozen over millions of years. Beneath that ice shell, evidence strongly suggests, lies an ocean of liquid water. Not a small ocean, a global ocean, possibly containing twice as much water as all the oceans on Earth combined. An ocean that has existed for billions of years, kept liquid by the tidal heating generated as Jupiter's gravity flexes and stretches the moon's interior. Life on Earth began in the oceans. Wherever we find liquid water on our planet, we find life. The deep-sea hydrothermal vents, far from sunlight and photosynthesis, teem with organisms that derive energy from chemical reactions with volcanic minerals. Could similar life exist in Europa's ocean? We do not know. But it is possible. And that possibility drives some of the most ambitious exploration plans currently under development. NASA's Europa Clipper mission, launched in 2024, will conduct detailed flybys of Europa, analyzing its ice shell, searching for plumes of water vapor that might erupt from cracks in the surface, characterizing the environment around the Moon. But here is the cruel irony. To study Europa, we must brave Jupiter. Europa orbits deep within Jupiter's radiation belts, the same charged particles that would kill a human within minutes continually bombard Europa's surface, breaking apart molecules, creating complex chemistry, and posing severe challenges for any spacecraft that ventures close. Europa Clipper will not orbit Europa directly. It will orbit Jupiter, making repeated flybys of the Moon, dipping into the intense radiation environment, collecting data, then retreating to less hostile regions to transmit its findings and recover its systems. The spacecraft carries a titanium vault to protect its electronics, similar to Juno's. It is designed to accumulate radiation damage over its mission lifetime, operating until the cumulative dose finally exceeds what its components can survive. Even in orbit around Jupiter, hundreds of thousands of kilometers from the planet's cloud tops, the environment is hostile enough to kill spacecraft. We cannot land on Jupiter, but Jupiter's influence extends far beyond its atmosphere, creating a zone of danger that encompasses its entire Moon system. The Juno spacecraft, as of this recording, has survived nearly a decade in Jupiter's radiation environment. It has completed dozens of close passes over the planet's poles, each time plunging through the radiation belts and emerging with new data. Juno has revealed the polar cyclones. It has mapped the magnetic field. It has measured the depth of the Great Red Spot. It has provided evidence for the fuzzy, diffuse core. It has discovered new aspects of Jupiter's atmospheric dynamics that continue to challenge our models. The mission was originally scheduled to end in 2021. NASA extended it. Juno continues operating, though its instruments show increasing signs of radiation damage. Eventually, like Galileo before it, Juno will be commanded to plunge into Jupiter's atmosphere, destroying itself to prevent any possibility of contaminating the potentially habitable moons. Every spacecraft we send to Jupiter is a one-way mission, not because we cannot bring them back, but because bringing them back would be pointless. The radiation, the distance, the fuel requirements make return trips impractical. These machines are designed from the start to die at Jupiter, and yet we keep sending them. We keep building new probes, new instruments, new systems to withstand the radiation a little longer, to measure conditions a little more precisely, to see a little deeper into the mystery. Because Jupiter, for all its hostility, for all its impossibility, continues to reveal secrets that transform our understanding of the cosmos. Every data point from Juno, every measurement from Galileo, every observation from Voyager and Pioneer adds to our knowledge of how planets work, how magnetic fields form, how atmospheres behave under extreme conditions. Jupiter is a natural laboratory for physics that we cannot recreate in any facility on Earth. The pressures inside Jupiter exceed anything we can achieve in laboratories. The temperatures span ranges that no material can survive. The magnetic fields dwarf anything we can generate with our most powerful magnets. Jupiter performs experiments for us, experiments that last billions of years, experiments that we can only observe from the outside, and every observation raises new questions. Why is the core so diffuse? What maintains the polar cyclones in their geometric patterns? Why is the magnetic field so asymmetrical? What drives the atmospheric bands? How deep do the storms extend? What is happening in the metallic hydrogen layer that we can never directly observe? Jupiter does not give up its secrets easily. It reveals them slowly, grudgingly, one dead spacecraft at a time. There is a Japanese word, mono no aware, that roughly translates as the pathos of things. It describes the bittersweet awareness of impermanence, the melancholy beauty of things that do not last. Every image of Jupiter, every measurement of its atmosphere, every map of its magnetic field was purchased at the cost of a machine that no longer exists. Pioneer 10 is silent, drifting through interstellar space. Pioneer 11 is silent, heading in the opposite direction. Voyager 1 and 2 carry on, but they left Jupiter behind decades ago. Galileo was deliberately destroyed. Juno will follow. These spacecraft gave us everything they had. They traveled billions of kilometers. They survived environments that would kill any living thing. They transmitted their final data even as their systems failed, even as the physics of Jupiter finally overcame their engineering. There is something profound in their sacrifice. These are just machines, yes, metal and silicon and wire. They do not experience pain or loss or regret, but they were built by humans, programmed by humans, sent to Jupiter by humans who wanted to understand a world they could never visit themselves. Every photograph of Jupiter's swirling clouds was taken by a camera that will never return. Every measurement of its radiation belts was made by sensors that absorbed the same radiation they were measuring. Every discovery about Jupiter's interior came from instruments that were slowly being destroyed by the very conditions they were studying. This is what it means to explore the impossible. Not to conquer, not to claim, simply to learn and to accept the cost of learning. We have sent 5 spacecraft to orbit Jupiter: Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, Galileo, and Juno. Only one of them carried an atmospheric probe. Only one of them sacrificed a piece of itself to the planet's interior. There may be future probes. NASA has studied concepts for Jupiter atmospheric entry, vehicles that could survive longer, descend deeper, measure more. The technological challenges are immense, but not necessarily insurmountable. Perhaps someday we will send another probe into Jupiter's depths, a more advanced machine that can withstand 100 bars or 1,000 before being destroyed. But no probe will ever land. No probe will ever reach the bottom, because there is no bottom to reach. Jupiter has no surface. This is the fundamental truth that makes landing impossible. Not the radiation, not the pressure, not the temperature, not the gravity. These are obstacles that might someday be overcome by technologies we cannot yet imagine. But the lack of a surface is not an obstacle. It is a category. Jupiter is not a world with difficult conditions for landing. Jupiter is a world where the concept of landing does not apply. You cannot land on a cloud. You cannot land on an ocean. You cannot land on a gradient that extends for tens of thousands of kilometers, continuously becoming denser and hotter and more extreme until the matter itself behaves in ways we have never directly observed. Jupiter is the universe's way of showing us that our assumptions about worlds are parochial. We grew up on a rocky planet with a solid surface. We evolved to walk on ground. Our entire conceptual framework for understanding places assumes that places have flaws. Jupiter does not have a flaw. And that simple fact, that absence, makes Jupiter forever alien, forever unreachable, forever impossible to land on. The night sky tonight, depending on where you are and what time you look up, may contain a bright point of light that does not twinkle like the stars around it. That is Jupiter, 480 million miles away, give or take, depending on where both planets are in their orbits, a world so large that 1,300 Earths could fit inside it, a world so massive that its gravity shapes the entire solar system, a world so hostile that every spacecraft we have ever sent to study it has been destroyed. You cannot land on it, but you can look at it. You can see the same light that Galileo saw in 1610, the same wandering star that ancient peoples named after their king of gods. You can know that behind that point of light lies a world of complexity and violence and beauty that humans will never directly experience. Perhaps that is enough. Perhaps the knowing is enough. Perhaps sending our machines to die in Jupiter's depths, returning data until their final moments, is the appropriate relationship between humanity and a world we were never meant to touch. We reach out, we learn, we sacrifice our proxies, and Jupiter remains, unchanged by our attention, indifferent to our curiosity, spinning through the darkness for another 4 billion years. The impossible planet, the place with no bottom, the world that reminds us, every time we turn our instruments toward it, that the universe is vastly larger, stranger, and more hostile than we can truly comprehend. And yet we keep looking, we keep sending, we keep trying to understand. Because that is what humans do. We reach for the impossible. We send our machines where our bodies cannot go. We sacrifice silicon and metal and radio waves for the privilege of knowing a little more about a cosmos that does not care whether we know or not. Jupiter will never welcome us. But perhaps, in some small way, we have welcomed Jupiter, and that will have to be enough.